My name is Elena McHale, and I will be presenting the work of Thomas J. McCabe on a complexity measure. McCabe was not on Google Scholar, so I couldn't find his H-index or a better picture of him, so I used what was in the paper. He received his MS in mathematics from the University of Connecticut in 1964. He worked for the Department of Defense at the time of this paper. He had also served as a captain on the Army Security Agency, engaged in large-scale compiler implementation on optimization during his military leave. This paper was in the IEEE Transactions of Software Journal in Volume 2, Issue 4 in 1976. I couldn't find the paper citations for a similar reason why I couldn't find the information on Thomas. The research question that this paper begged was, is there a way to modularize a software system so it is testable and maintainable? Off of that, we may also ask, are there restrictions to the development? His motivation for the development was the issue of spending half of development time in testing, spending a lot of money on testing, and the need for modularization to identify software modules that will be difficult to test or maintain. It should be said that one practice was used before this paper, and that was just to limit the program in physical size, which of course is not always adequate. So the approach that this paper takes into the research question is to measure and control the number of paths through the program. We will need a few mathematical establishments to do this. The first definition is the cyclomatic number V of G of a graph G with n vertices, e edges, and p connected components is V of G equals E minus n plus p. The second information that we need is a theorem that states in a strongly connected graph G, the cyclomatic number is equal to the maximum number of linearly independent circuits. So with this information, we can use an example program, control graph to the right here, to create an equation for the maximum number of linearly independent circuits. So this graph would actually represent the equation 9 minus 6 plus 2. So the reason for this is there are 6 vertices, or we could name them A through F, 9 edges, or connectors, as I usually describe them, and 2 vertices that are connected to start the flow. So let's use that same diagram and number the edges this time. So take 5 independent circuits that can be created from G. We will use ABEFA, BEB, ABEA, ACFA, ADCFA, which was in the paper. You can then create a vector out of these independent circuits. So I will just go through the ABEFA for an explanation. So traveling from node A to B, we use path 1, so we will mark that path 1 was used one time in the vector. To go from B to E, we will use path 4, so we can mark that under the 4 in the vector. From E to F, path 8 is used, and we're going to mark that accordingly as well. And then finally, from F to A, we use the path from the connected components, which is path 10. So we will mark a 1 under the 10. So we will mark the unused paths as 0. If you were to take a path more than once, you would want to mark how many times you use that path instead of simply marking it as 1. It's not really like a true or false type of vertice. So overall, the strategy is to measure complexity by computing the number of linearly independent paths, control the size of the program through the upper limit, and to use cyclomatic complexity as a basis for testing methodology. So the control graphs on this slide are matched with the complexities. The cyclomatic complexities are created the same way as the example that we just did on the other slide. There is a way to automate what we've been talking about so far. A tool was built to run on PDP-10 using the flow command written in APL. First, flow should first flow would input the source code, then break the job into distinct subroutines and analyze and control structure of each subroutine. The flow between blocks is represented by an n by n matrix. There will also be a produced block listing of the original program outputted. So here you can see the blocks, the n by n matrix, and its according program control graph. In this paper, he has specifically broken down Fortran programs. Just that is his experience that he's used. So in his experience, an upper bound of 10 was used for cyclomatic complexity. So when complexity would exceed 10, programmers either had the option of modularizing subfunctions or redoing the software. Situations where 10 is unreasonable, however, is when many independent cases follow a large case statement, but in this case, the limit could be exceeded. There are a few specific conditions why an unstructured program construct would work best, but we're not going to try to use them unless we absolutely have to. These unstructured constructs should only be used under special circumstances. So here we have 4 control structures that are found to generate all non-structured programs. So the first one, A, represents branching out of a loop. B is branching into a loop. C is branching into a decision. And D is branching out of a decision. There are several results that are made from these structures. Result 1 is a condition that a program is unstructured, is that it contains a subgraph of either A, B, or C. Result 2 is that any unstructured program must contain at least 2 of the graphs A through D. Result 3 is a program is unstructured if it contains at least one of AB, AD, BC, or CD. Result 4 is off of that, saying that the cyclomatic complexity of a non-structured program is at least 3. Result 5 is a structured program can be written by not branching out of loops or into decisions. Result 6 is similar by a structured program can be written by branching into loops or out of decisions. And then result 7 is a structured program is reducible, and result 8 is the essential complexity of a structured program is 1. And you can find these in the case of course if you want to look into them further. Okay, so getting into testing, if there is a program P with a complexity V and the number of test pass is AC, or that stands for actual complexity, then we know if AC is less than V, one of the 3 conditions are true that were detailed in the paper. I'll get into them here as well though. So those conditions are there is more testing to be accomplished, program flow can be reduced, or portions of the program can be reduced into inline code. So in this example, we take 2 paths. We'll use E, A1, B, and C2, and X. And then we'll also use E, A2, B, C1, and X. So in this case, AC is 2 and will be less than B. We won't go through that whole process to figure out B since we have already detailed that on other slides. So we know that one of the 3 conditions holds in this case since AC is less than B. And in this case, G can be reduced by taking out B, which will be G1 graph on the right here. So why would you do this exactly? This is helpful to programmers who need to document flow graphs and show different paths tested. The conclusion we can draw is that a method was created for computing the number of possible paths. The paper was also able to identify a way to modularize a software system so that it's testable and maintainable. It only really ran into the roadblocks of unstructured program code, which probably could be looked into further. I'm not sure if there's additional work already done on that. So I found the paper relatively easy to follow along with. There's many examples and diagrams provided to practice on. I also liked how the paper wasn't overcrowded with proofs, like a lot of other research papers you would probably read in the math field. If you wanted to look into the proofs, you definitely could, but the author did do a good job at recognizing more importance in the overall modularization tactics instead of just putting mathematically heavy detail through the proofs. Here's my reference, and I look forward to your discussion.